Good morning, AP Physics 1. Hope everything worked out with the last video. Hope you got to see it. You turned in your homework. I haven't checked all that yet, but I will. I know some of you have started sending me emails, so that's good. Today, I want to review for a few minutes Chapter 18 because you're taking a test on Chapter 18 tomorrow, which is Wednesday. And that test is in Blackbaud. You will be able to take it anytime on Wednesday. I've never given a test on Blackbaud, so I don't know how this is going to work, but hopefully you'll be able to find it. You'll take it in your Surface. You will begin, and once you click begin, you have the amount of time it tells you to do that, and then it goes away. If you try to exit, or if you do exit anytime before you're finished, well, it's over. You can't go back to it. That's what I've been told. We'll find out. We'll see how it works. Your other homework is assignment C, which will be due Thursday. Now, I'm going to pray, and then we're going to move on with this class. Hopefully this lecture will not last more than 30 minutes total. Lord, I pray that you will watch over us as we move through what seem to be pretty trying times. I ask for your protection and for your strength and for good health for each of my students. I pray, Lord, that you will watch out for them and that they will learn to trust you even more through this. Bless them as they learn some physics. Amen. All right. Chapter 18. Not going to spend much time because we've already covered this entire chapter, but it's been a while. You might remember that the elementary charge is 1.6 times 10 to the negative 19th coulombs. That's the smallest charge anything can have. That is the amount of charge in one electron, also in one proton. You also remember that opposites attract, and like charges repel. Very important there. The magnitude of this force, this is a vector that represents force, the magnitude of the force can be calculated this way: KQQ over R squared, absolute value of the Q's. The direction of F comes from, is it attracting or is it repelling? So you don't need any signs on the Q's. R is the distance between them. K is 9 times 10 to the 9th, which is also on your constant page. All right. Which reminds me, when you take the test, of course, hopefully you have a copy of the equation sheet that I've given you. I might send one out that you can have digitally, and in case you don't have yours. That's a good reminder for me. I'll do that. The other thing we talked about, F is vector, of course, but we also talked about the fact that charge is conserved, and so it's common to get questions where you have these spheres that have charge on them and they touch, and charge moves from one to the other. Or perhaps there is an ebonite rod that is charged and it comes near or it touches, induction or conduction. So go back and look at all the things that we've studied in relation to this. It's not a long chapter. It's only, or the part that you need to know is not long. So go over this and prepare yourself. And then once you start the test, please go by the honor code. It is a test. You're not to get help from anyone else. It's a test, just like if you were taking it in my classroom. So I trust that you will do that. Now, that's the test. Second thing we need to talk about today is just a few additions to yesterday's lecture over the first 4 sections in chapter 20. A few additions. One is you have heard of AC and DC, alternating current and direct current. In AP Physics 1, all we study is direct current. There is a section on alternating current in your textbook. We will not cover that because it's not on the AP exam. Direct current simply means a circuit where current is flowing from the positive terminal through through a conductor, the wire, and through some resistor like a light bulb and back to the negative terminal, but it only moves in one direction. In this drawing, it's moving clockwise. It does not go backwards. Okay. That's all you need to know about that. DC is what we are dealing with. The next thing is when you look at the equation I gave you yesterday on resistance, where resistance of the resistor can be calculated as rho L over A. Rho is the resistivity of the material the wire is made of. If it's a copper wire, you can look up copper in that chart in your book and find out what resistivity for copper is and plug that number in here. The thing about resistors is resistivity itself can change with temperature. If I were you, I would look in your book at page 583. You should have done that already when you read sections 1 through 4. But on that page, it mentions that temperature can affect resistivity, which means it affects resistance. The resistivity of a metal, for example, will increase when it gets hot. And so if that changes, sometimes R can change. If you ever see a question that asks you, is this circuit ohmic, O-H-M-I-C? Is the wire ohmic? Is the circuit ohmic? Is the system you're looking at ohmic? If it is, here's what that term means. Ohmic means R is constant. It is not changing. In real life, R is not always constant, which means the circuit is not always ohmic. But most of the time in physics problems that you'll work on a test, the assumption is that R is not going to change. The copper wire is not getting longer. It's not changing in its thickness. And so we also assume resistivity is not changing because it's still copper. And so we ignore the fact that the temperature might change. So I'm just letting you know that if you ever work a problem and you get 2 different values for R at 2 different times, then you would have to assume that the circuit is not ohmic, because R would be constant if it's ohmic. That's all I need to tell you about that. Next thing is that there are symbols you have seen probably already in your textbook for some of the things we've talked about. So let me make sure you have those. If you see 2 parallel lines, but one's long and the other's short, that represents a battery. That's a source of EMF. That's a source of potential difference. That's a battery. And if you see a wire, if you just see a line coming out of it, that represents a wire attached to the battery. And when you see this symbol for the battery, the long line always represents the positive terminal of the battery. The short line represents the negative terminal. So this side over here is high voltage. Over here is lower voltage. You have learned that current flows from high to low potential. Therefore, you know that in this circuit, current is flowing clockwise. All right, that's what the symbol for battery and wire means. Now, if you see a symbol up here that looks like this, That is a resistor. That could be a light bulb. It could just be an object that a coil of some kind that gets hot, like in an electric heater. But it's something that uses up the electrical energy. It's a resistor. And so that has some number of ohms. This has some number of volts. It's a battery. All right. There's other symbols we will talk about later. When we get to circuits, we'll talk about series and parallel circuits, but that's coming up later, not today. Final thing is a superconductor. And then we're going to go over some of the homework problems, and that will be it for today. But what do we mean by the term superconductor? You may have heard that term before. It is a relatively new area of physics that seems to have some potential. Superconductor is a conductor, something that electricity will flow through, like a wire, but it is a conductor where R, the resistance in it, approaches zero. That is, it's very low. Very, very little resistance at all, which means current has no trouble flowing through it whatsoever. A lot of studies on superconductors. Right now, we are still at a place where they have developed superconductors where R basically is zero, but they only work at very, very low temperatures. I mean, approaching absolute zero, temperatures that are that cold. And they continue to develop new materials that will work at slightly warmer temperatures. And so we have some that will work above single digits on the Kelvin scale, but still very low temperatures. That's all you need to know about superconductors. And that is that. All right, we're going to go over some homework next. I have chosen a few problems from assignment B that we will go over, starting with number 3. By the way, number 1 just uses I equals Q over T. I think you can probably deal with that, but let me know if you need help. Number 3, again, uses I equals Q over T. In this case, you have a 0.11 amp current through normal operation and a 0.067 amps in standby mode. This is a fax machine. The machine uses 120 volts. In 1 minute, how much more charge passes through the machine in the normal mode? So this would be I equals Q over T, which of course Q is the question, and they gave you I and the time. And so in this case, Q would be equal to the current, I, times the time in seconds. Q equals it. And so what do you have, Kelvy, what do you have for? I should have told you get your homework out. Yeah, pause this and get your homework out if you haven't already. And turn in your books to page 634. So you'll see the questions. Now, Kelvy, what do you have for number 3? A. 2.6 coulombs is correct. Yes. You simply do it twice. Now, make sure you put the amps in seconds. I'm sorry, the time in seconds, the current in amps, and simply multiply it for normal and multiply it for standby and subtract. And when you subtract, you'll get 2.6 coulombs. It's actually 6.6 minus 4.02. Now, part B, that was A. Part B, you're asked how much energy, how much more energy is used. So you're taking this answer and you are finding out how much energy that would be. And if you don't know how to do that, let me refer you again to this equation I gave you yesterday. V is U over Q, which is not on your equation sheet, but if you get a question like part B, you need that because here's the energy. It's going to be Q times V. The Q is 2.6 and the V is 120 volts. That's how you do part B. All right, and that answer is 312 joules. Now, let's try number 6. The answer to number 6, I believe, for part A, does number 6 have a part A? Don't know. The answer to number 6, I believe, is 6.2 times 10 to the 4th joules. Yes, I believe that is the answer. And here's how you could, let me erase the board. So here's one way you could work this problem. Start with Ohm's law, I equals V over R, to get the current using the numbers they gave you, 120 divided by 14. And then you could use I is Q over time to come up with Q. And in that case, Q equals 514 coulombs. And that is simply this current times 60 seconds gives you Q. And once you get Q, you could then do the same thing we did in the last problem, U equals QV. Because they gave you the voltage of 120 volts times this 514. And that will give you the right answer, which is 61,700, rounded off, joules, or 6.2, as I said, times 10 to the 4th. Here's another thing you could have done. Let me just show you that power is IV, and another version of that, we went over the different versions yesterday, so let me remind you, one of the versions of that power equation was V squared over R. I mentioned that because this problem gave you V and R. Yes, it gave you V and R, both in the problem. So you could calculate the power from that, and then what you know is that power is also energy divided by time. It's work divided by time, or some form of energy divided by time. And the question here is the energy. So you could have done it this way. V squared over R, and then take that number and use 60 seconds for the time and solve it for U. Another version of this is, since power is energy divided by time, that's what this is right here. And power is IV. If I cross multiply and solve this for energy, it's power times time, of course, but power is IV. So sometimes I remember this equation, that E equals VIT. Here it is. Now that's not on your equation sheet. It simply comes from energy, from this energy, U, which here I wrote as an E. Energy is power times time. And power is IV. So IV times time. Here's IV times time. VIT. Yeah, VIT. So anyway, 6.2 times 10 to the 4th joules for number 6. Let's do another one. All right, number 12 is another even numbered problem. It helps me if you would read for me. So how about, Eric, would you read out loud number 12, please? Everybody else follow along. Go ahead, Eric. A cylindrical copper cable carries a current of 1200 amps. There's a potential difference of 1.6 times 10 to the negative 2 volts between 2 points on the cable that are 0.24 meters apart. What is the radius of the cable? Radius of the cable? Well, that has to do with the thickness of the cable. So what you're already thinking about is, where in the world can I get something related to the thickness of the cable? And that's going to come in with this equation, rho L over A. If I can get the cross-sectional area, then I can get the radius, can't I? which is the area is pi r squared. Okay, well, how do I get everything I need here? I go back to Ohm's law, V equals IR, or I equals V over R. And in this, the problem gives us the voltage, and it gives us the current. And the voltage was 1.6 times 10 to the negative 2. And the current was 1200 amps. And if I solve that for R, I get a resistance of 1. Here it is. I get a resistance of 1.33 times 10 to the negative 5 ohms. That's R. Well, now I've got a number to plug in down here for R, and I can look up rho for, Eric, what was this? This was copper. Look up rho for copper, and I believe that's 1.72 times 10 to the negative 8, and the length is 0.24. So I've got everything I need here to solve for area. And area, again, is pi r squared. So in this case, I got an area of 3.1. Plugging in this r here, the rho from the chart for copper, the length of 0.24. The area came out to be 3.1 times 10 to the negative 4th meters. And that, of course, then is pi r squared to solve it for r. We'll divide that by pi and take the square root. I get an answer of 0.0099 meters. Please remember these zeros are not significant. So even that only has 2 significant digits in it. Don't round it off to 1. Okay, there we go. That's number 12. Let's do one more, perhaps number 15. So what did you get for number 15 as an answer? Junha, what do you have? Yeah, tell me what you have. That's the same thing I have, Junha. That is 1.64. Now that's a ratio. It doesn't even have a unit. That's correct. You did a good job on that, Junha. Here's what the problem says. And Eric, you can read this one too. Go ahead. 2 wires have the same length and the same resistance. One's made from aluminum. You can look up aluminum in the chart to get resistivity. The other from copper. Obtain the ratio of the cross-sectional area of the aluminum to that of the copper. What we want is this is number 15. What we want is the ratio of their areas. And it was the area of the aluminum to the area of the copper. So that's what we want. What I would say is, since R is equal to rho L over A, here's how I would approach this. This is the equation I know I'm going to use because there's my A. And what you were told was they have the same resistance. So this for the aluminum has to equal this for the copper. This for aluminum, this for copper, because the R's are the same. And what you also know is that they have the same length. Divide by L, they're the same. And so what's left is rho for aluminum over the area is equal to rho for copper over the area. This is the aluminum, this is the copper. And now you can plug in those numbers from the chart and get this ratio, where the ratio of aluminum to copper here, aluminum to copper would be equal to the rho for copper divided by the rho for aluminum. Now, is that true? I think that's true. And again, somewhere on this paper, I have an answer. It comes out to be 2.82 divided by 1.72, which is 1.64. All right, we are going to do one more, number 27, the last one that you had assigned for assignment B. I'm going to read it this time. Eric, just relax. In doing a load of clothes, a clothes dryer uses 16 amps of current. I'm going to write down what's given, 16 amps for the clothes dryer, and at 240 volts. So V is 240 volts. And it takes 45 minutes. The time is 45, but times 60 would make it seconds. All right, times in seconds. Now there's a personal computer, in contrast, that uses 2.7 amps. So over here's my computer, and its current is much less, 2.7 amps, and it's at 120 volts. That's less as well. And the question, with the energy used by the clothes dryer, we need to find energy over here, because this is the clothes dryer. With the energy used by the clothes dryer, how long in time, in hours, time is the question now, could you use this computer to surf the internet? All right, we've got to find E. Now, you can do it the way I showed you before. That is, you could use P, well, yeah, here's one way. P equals V squared over R, and no, P equals IV, because that's what we have, and that's equal to energy divided by time, because power is energy divided by time. Solve that for E. It's pretty easy to see, though, that you could just put that together like this. E equals VIT, once again, because there's your V, there's your I, and here's your time. If you multiply all of that together, you get energy in joules. And where is my answer sheet? Kaylee? What did I do with my answer? My answers. Ah, here they are. Thanks. Thanks, Kaylee. Now, no, that's not it. Where are they, Kaylee? I'm going to pause and look for it. All right, well, I found it. Thanks, Kaylee. Yeah. Suho, what did you get for an answer on 27? Suho. Correct. It is 8.8 hours. Did you get that, Reed? Are you saying yes because you got that, or because you know that Suho is usually right? Both. Good answer. Here are the numbers I came up with. The energy multiplying V times I times T comes out to be 1.037 times 10 to the 7th joules. That's a whole lot of energy. It's a dryer. They use lots of energy. Don't round off this number in the middle of a problem very much at all. Keep at least 4 significant digits, or 5 or 6. You're going to use this back over here, because the question was, now if we had that much energy for the computer, how much time would it run? And once again, you can use E equals VIT if you want to shorten, put some of those other equations together. I find this easy because you now have a number for energy. It's 1.037 times 10 to the 7th, and that's equal to V for the computer is 120. By the way, your standard plugs in your house are at 120 volts. That's why they use that a lot in the problems. And the dryer in your house uses 240. It has its own special plug. So I'm just letting you know why these numbers are here. These really are what the numbers would be. The I is 2.7, and you're going to solve that for time. Of course, the time will come out in seconds when you calculate that. And I believe I did that, and I got a time of 31,697.5 seconds. So divide that by 3,600 seconds per hour, and you will get 8.8 hours. That's correct. Okay, That's your homework. You don't have any other homework due tomorrow, Wednesday, to take a picture of and email to me. Assignment C is going to be due Thursday. That'll be the only homework due Thursday by 11 o'clock. However, tomorrow, Wednesday, you need to make sure you are taking the test. Pick a time when you can sit down with your Surface, and I believe, I haven't finished it yet, but I believe there are going to be 2 different tests. One is for multiple choice, and the other for free response. So take them both. Good luck on that. I love you guys. I'll see you soon. Bye.